In the previous lessons, we learned about chemical reaction, and we know that some chemical reactions are very explosive. Well, today we're going to look at why is it explosive for some chemical reaction, but why the other chemical reaction is not. And basically, it's all about energy. Well, energy is the ability to transfer heat or to do work. And thermodynamics is the study of energy changes in physical and chemical processes. Well, to understand how energy changes in a physical and chemical process, we need to understand the first law of thermodynamics. Basically state that the total amount of energy in the universe is fixed. Well, the word fixed means it does not change or same. Then we have another term called kinetic energy. Well, this type of energy of an object is referred to the energy of motion. Well, think of motion, let's talk about velocity, how fast it goes. Then we have Kelvin temperature. And one thing you need to realize that when we talk about energy, we are talking about the energy in terms of Kelvin scale. And all your math and all your calculation will be done in terms of Kelvin. So if you have Celsius or Fahrenheit, you need to convert to Kelvin. And what's so special about temperature? Well, the Kelvin temperature of a system is a measure of average kinetic energy of the particles that make up the system. So basically, if you have particles in a system at lower temperature, it would move slower. It would have a lower average kinetic energy. Where if you have particle at higher temperature, it would move faster. Let's compare lower temperature versus high temperature. And if we look at lower temperature, let's draw a random particles, and we know that this line here represents the motion or the velocity of the particle. Well, if the same particle exists at higher temperature, you will see a longer line. So this longer line represents it is moving at a faster velocity and has greater motion, which is greater average kinetic energy. Now, what happens when you have two samples at different temperature are in contact with each other? That means they touch each other. Well, the energy always flows from a system of higher temperature to a system of lower temperature until both substances have the same temperature. And we have a term when two substances have the same temperature, and that is considered as thermal equilibrium. Now, if we are to illustrate this concept, of course, I just write the term hot to cold until both of them have the same temperature. Now, let's look at our chemical reaction in a different terms. Well, we have the term system. The word system is basically a sample, which is our chemical reaction, or a region being observed. So this is our focus or study object. And we are going to compare this in terms of, when we talk about changes in energy, it's basically comparing the system versus the surrounding. And basically everything else surrounding a system is the surrounding. For example, let's illustrate this. Let's say I have a system where this would be my system. Notice how it has a boundary, right? This is my focus. Well, the rest of it is going to be surrounding. So let's look at an example. Now let's look at the term system and surrounding in terms of chemical reaction. Well, first of all, this becomes more complicated. Well, if we have this as a beaker, and this would be our water, and if we add something in here, then we add something to water, so we have a chemical reaction, okay, in this water. Well, this chemical reaction is going to be the system, and the water would be the surrounding. And of course, this would be the simplified version of understanding chemical reaction happen in a solvent. In most cases, the substance will be dispersed throughout the solvent. We have a solution, and the reaction just happen in the solution. Now let's get to the fun part of energy. And what we have here is work, which is represented by W. And basic work is the product of a force acting on an object or a system. And just like energy, the unit for work or energy is in joule. And joule is represented by the letter J. So work, remember, we define energy is the ability to do work. So therefore, work is energy. And the formula for work is, here we have work equal to negative P times delta W. Well, P, what is P? We know it is pressure. But we are referring to the external pressure. Then we have delta. That is basically changes. And delta is always final minus initial. Since we are talking about delta V, what does V stand for? That would be volume. So we have delta V. Delta V is equal to volume of final minus volume of initial. And if we look at the equation of work equal to negative P times delta V, well, if the work is negative, okay, work is equal to negative, that means the system is doing work on the surrounding. So it's releasing energy. Think of that way. Okay, negative is releasing energy. Where if work is positive, it is absorbing energy. Well, if it's releasing energy, where is it going to release to? It's going to release energy to the surrounding. And if it's absorbing energy, it's going to absorb energy from the surrounding. Now, how are we going to be able to have a negative work? And the only way that's possible is when you have a positive changes in V. Okay? But because if change in volume is positive and a positive times a negative, that would give you a negative answer. But let's look at when work is equal to a positive answer. And the only way that's possible is when you have your delta V is equal to negative. Because negative times a negative give you positive. Where up here, when you have a positive times a negative, that would give you a negative answer. And think of this in terms of this right here. When a system expands, that means your volume change is positive. The system is doing work on the surrounding, just what we said here, right? When the system has a positive volume changes, it releases energy to the surrounding. It's basically doing work on the surrounding, where if the volume change is negative, that means it gets smaller, it gets contracted. The surrounding is doing work on the system. Or think of this way, the system is absorbing energy from the surrounding. So that's an important concept to understand. Now let's look at the easiest part of all. It's basically plug into the equation of work and solve for work in terms of the unit joule. A piston expands from a volume of 1.5 liter to 3.0 liter at constant external pressure of 1 atm. How much work is done? Is the work done by the system or on the system? Well, first of all, let's plug into the equation. Work is equal to negative P times delta V. And we know negative P, well, in this case, negative stay the same. P is 1.00. And change in V, again, is always final minus initial. So in this case, we have 3.0 minus 1.5. And all we have to do this is equal to 1.5. Plug into a calculator. What do we have? What is negative times 1 times 1.5? And the answer is negative 1.5. Which in this case, the unit for work is always in joules. Let's try another problem. A balloon expands from a volume of 0.1 liter to 3.0 liter at a constant external pressure of 1 atm. How much work is done? So in this case, if it's negative, that means it's release energy, right? Release energy. Therefore, the work is done by the system on the surrounding. Let's try another problem. A balloon expands from a volume of 0.1 liter to 3.0 liter at a constant external pressure of 1 atmospheric pressure, or ATM. How much work is done? Is the work done by the system or on the system? Same thing. Work is equal to negative P times delta V. In this case, negative was P. P is 1.2. What is our delta V? Well, in this case, the final volume is 3.0 minus the initial, which is 0.1. So in this case, this is equal to 2.9. That's a change in volume. And again, you know that the change in volume is positive. That means the system is doing work on the surrounding. It is releasing the energy to the surrounding. So therefore, we have negative 1.2 times 2.9. And this equal to negative 3.48. And that's a unit in joule. And because of this negative right here, that tells you that the system is doing the work. So the work done by the system. Let's try the last problem. A balloon shrinks from a volume of 3.1 to 0 liter at constant external pressure of 1 atm. So it's the opposite of that, right? How much work is done? Is the work done by the system or on the system? Same thing, W equal to negative pressure times change in V. Well, negative pressure, in this case external pressure, is 1.2, and your change in V, the final is 0 minus 3.1. In this case, that will give us a negative 3.1. So a change in volume is a negative 3.1 instead of a positive before, right? So therefore, let's plug everything into a calculator. And what we have here is 3.72 joules. And if you notice, this is positive. So because it's positive, it is absorbing energy from the surrounding. Think of positive is gain. And negative is loss or release. So in this case, the work, it is done on the system by the surrounding.